Yeah, so this talk is called Benchmarking GPU Clusters with the Jülich Universal Quantum Computer Simulator. As I already said, my name is Dennis Willsch, and this talk basically has a part of what I presented at GTC 21. That's why we have GPUs in there, but I've adapted it slightly, so let's start going. And yeah, as Tara said, please interrupt me and ask questions whenever you want. All right, so here are the contents. So first, I'll introduce quantum computing, and I'll put a focus on the linear algebra perspective. So the take-home message sort of would ideally be that quantum computers are nothing but small matrix or large, in some scale, matrix vector multiplicators. So there's a lot of matrix vector multiplication, and you have this in all kinds of quantum computers when you simulate them, when you simulate the physical realizations, and you'll see during the talk how that turns out. Then I'm going to introduce JUQCS. That is the Jülich Universal Quantum Computer Simulator. That is a massively parallel simulator that runs on supercomputers. And we also use this in collaboration with Google for the quantum supremacy experiments. Then I'll introduce JUQCS-G. That is the GPU version of this simulator. And finally, I'll talk about JUQCS. That is another simulator whose goal is not to simulate the ideal quantum computer, but a physical realization to understand to what degree do real experiments at the moment implement this quantum computing paradigm. All right, so let's start with the ideal gate-based quantum computer. So ideal meaning that we want to differentiate this from the physical realization. So now we're talking not about Google's Sycamore chip here, but about the ideal gate-based quantum computer, what it's supposed to work like. So what does it do? It runs a quantum circuit. So what does it mean actually? So a quantum circuit is what we see in a diagrammatic scheme here. And what it actually means is that it performs matrix vector multiplications. And those matrix vector multiplications are sparse, complex, and unitary. That means they involve a lot of unitary matrices, but most importantly, they are huge. So the vectors and the matrices involved in these multiplications are huge, and that's what makes it difficult to simulate and to work with. So what kind of sparse unitary matrix vector multiplications? The vector in these multiplications is the state of the quantum computer, and that is basically just a huge bunch of complex numbers. So for n qubits, for an n qubit system, we have 2 to the n complex numbers. And we have them all in a large array on the supercomputers distributed over several GPUs. And the goal is to keep track of these numbers, which describe the state of the quantum computer during the computation. The matrices in these multiplications are the quantum gates. And you'll see that each quantum gate corresponds to one sparse unitary matrix that sort of does some things with these complex numbers here. So let's look at an example. So we take 4 qubits, that means 16 complex numbers, and we look at this quantum circuit here that we've also seen on the previous slide. And this means that, so time proceeds from left to right, and this is sort of a program for a quantum computer. So it starts on the left-hand side with the initial state of the quantum computer given by the all zero state, which just means that almost all of the complex numbers are 0, so 15 numbers are 0, and only the first one is 1. And then as we go through the quantum circuit, which sort of describes the program that we run on a quantum computer, we do these operations. So for example, let's say we've advanced to this state here. This is a Hadamard gate, and what this means for all these complex numbers is the following. So it's a Hadamard gate on qubit 1, so we have 0, 1, 2, 3, and it means that for all values of Q3, Q2, Q0, these are the indices into all these complex numbers. So for all of these indices from 0 to 1, we perform this 2x2 matrix update. And this is quite a lot of 2x2 updates, right? So, okay, for the 4-qubit quantum circuit, it's not that much, but if you imagine you have a 40-qubit quantum circuit, then it's a lot of 2x2 matrix vector updates. And if we carry that through all these gates here, at the end, we obtain the final state of the quantum computer. So all these complex numbers now have some specific values, and that describe the result of the computation. So now the interesting question is, what would a hardware realization of a quantum computer return? So the naive assumption might be the quantum state after all these sparse matrix vector multiplications. And that is not what happens, because that would be 2 to the n complex numbers. So for 40 qubits, we would have 16 terabytes of complex numbers, and that is obviously a lot. So that is not what like Google's Sycamore chip spits out. What then? The answer is it only returns a single bit string. So for each of these 40 qubits, we only get a 0 or a 1, and all these complex numbers only describe the probability to find this particular bit string. So if we have this complex number here at the end, then its modulus squared would yield the probability to return a string of all zeros from the quantum computer. So that is a scheme that we see with every kind of quantum computer. We need to run the circuit repeatedly. So we do it several times, also like what Google did in their quantum supremacy experiment. You run the circuit many times, and from all the bit strings that you get out, you might be able to get some information on these complex numbers. And the goal is, of course, to write a quantum circuit that, with all these bit strings, gives some information about the problem that you want to solve. Because these complex numbers describe the state, but you cannot really access them if you're running on a real computer. That is on a real quantum computer, because on a supercomputer, of course, we have them, right? On a supercomputer, we can access them. And that's also what makes it interesting to simulate them on a supercomputer, because then we can really see what's going on. So I don't want to keep from you what this example circuit here actually does. This program for a quantum computer is a 2-qubit adder, which means that it does a transformation according to this recipe here. So we have an input number here. So these bits, zeros and ones, encode a 2-bit integer here, and Q2, Q3 encode another 2-bit integer. And after we've run this quantum circuit, we find the lowest, or the upper 2 bits, we find the result of the modular addition of these 2-bit integers. So that is a quantum circuit that's very attractive because it's easy to verify what it does, right? If you run this on a real quantum computing device, from the output, you can see whether it worked properly, whether you really have the addition here or not. And an example is here. For example, if you put this register to 2 and this one to 1, so this would be 1, 0 for the 2 and 0, 1 for the 1 here. Then at the end, you would expect a 3. That is the sum of these two integers in these 2 qubits, so in the bit string that you get out. And because this is a quantum circuit, it can also do superpositions. That means in this kind of funny notation, if you put as input in one register a superposition, this is just like a description of the complex numbers, like 3 complex numbers with the value 1 over square root 3. Then after the operation, you would find the addition of those numbers for all possibilities. So 2 plus 0 is 2, 2 plus 1 is 3, and 2 plus 2 is 0 because we are working modulo 4. So in terms of these complex numbers, it just transforms these 3 complex numbers, which are like 1 over square root 3, into these complex numbers. And how do we learn why this is the case? One option to learn why this quantum circuit does what it does is to simulate it with JUQCS. And that is what brings us to the simulators now. So what does a quantum computer simulator do? This now runs on a supercomputer like we have in Jülich here. And the answer is, as before, it runs a quantum circuit. And also this means the same as before. It performs many matrix vector multiplications. As we've just seen, for each of these quantum gates, we have a certain set of sparse matrix vector multiplications. So the difficult thing in simulating these circuits is now to manage all these complex numbers, because we've seen there's a lot of complex numbers that describe the quantum computer. So the answer is we distribute those complex numbers over multiple compute nodes. So the memory is actually the bottleneck in these simulations. Let's look at this example of 40 qubits. We have 2 to the 40 complex numbers to manage during the simulation. That is 16 terabytes. And we put them in packages of 64 gigabytes on several compute nodes. In this particular example, on 256 compute nodes. And schematically, this looks like this. So here we have our supercomputer with all these compute nodes. And then on the first compute node, we have all the complex numbers where the index has a 0 in these leftmost qubit indices here, and all the other remaining indices run from 0 to 1. So that is how we get to the 2 to the 40 in the end, right? Because we have all combinations of zeros and ones here. Then on the last compute node, which would here be the compute node with identifier 255, we then have all these complex numbers which have a 1 in the leading indices. And conventionally, for this kind of simulations, we call the leftmost qubit global qubits because they encode the identifier, like the compute node in the supercomputer, where these numbers are stored on. And the other qubits we call local qubits, and global and local also has a meaning because, as we'll see soon, something that happens on a local qubit is very simple. It only happens locally on one compute node. But some quantum gate that happens on global qubits, that requires transfer of data between these compute nodes. So this transfer is called Mpi transfer. Mpi is the system that does the memory transfers, the message passing interface. That's why we also identify these compute nodes with Mpi rank. That's sort of the keyword. So that's for the CPU-based version. Now we have a GPU-accelerated simulator, but basically there's not much different here. So instead of distributing all these complex numbers on the different compute nodes, we directly put them on all of the GPUs that take part in the simulation. So we have a bunch of NVIDIA A100 GPUs, so 3,744 to be precise, and each of them has a memory of 40 gigabytes. So if we were simulating a 40 qubit circuit, we could put all those numbers in packages of 16 gigabytes per GPU on the system. So schematically, this looks like this. We now have our compute nodes, and in each of these compute nodes, there are 4 NVIDIA A100 GPUs. And on the first GPU, we have all those complex numbers which have a 0 here. And on the third or fourth GPU, so GPU rank 3, we have all the complex numbers which have a binary 3, so the binary representation of 3 here, and that continues all the way up to the last of those 2 to the 40 numbers. For the simulation on the GPUs, the Mpi communication scheme is the same. So what do I mean by Mpi communication scheme? So Mpi, as I've just said, the message passing interface is necessary whenever we when we need communication between different GPUs. And Mpi is the system that takes care of transferring data between the GPUs. And this is necessary when we actually simulate the quantum circuit. So let's look at an example here. We now have distributed all these complex numbers across the supercomputer, so on all of these different GPUs. So these numbers in the quantum state are on GPU 0, then these numbers are on GPU 1, and all the way up to these numbers which are on GPU 255. And now say we simulate the quantum circuit, and we've come to this point here. So now we have to do a Hadamard gate. And we look first at a Hadamard gate that acts on a local qubit. So qubit Q30, we always count from the right. This would be Q0, and Q30 is somewhere here. It's within the local qubits. Then each of these GPUs has to perform this operation. So the Hadamard matrix was a particular 2x2 matrix, and then each GPU goes through all their complex numbers, and in pairs of 2, it performs this operation for them. So the first indices here encode the number of the GPU, and then it always, for all values of the other indices, it does this operation. And this is very simple, right? Because all the numbers that would need to be combined now with this quantum gate, with the local quantum gate, they are already on the same GPU. So we can just go do it, and then doesn't need to be any communication between the GPUs. Let's look at a brief example how this happens in the code. So here we have so this is Fortran code. Here we have a kernel that runs on a GPU, and let's look at how the GPU now does this. So this function gets as an input a mask, an identifier of what kind of pairs of complex numbers it needs to combine. And then it computes in a standard CUDA way the iteration index. It is just, it tells the GPU or this invocation of the kernel which of the two numbers it needs to combine. And then from this, it computes the two indices, like the index of the first and the index of the second complex number. And then it just does this very simple 2x2 matrix. So this matrix multiplication is written out in real and imaginary parts here. So now what is the difficult thing in this simulation? This comes in when we have a quantum gate on a global qubit. So let's look at an example of a Hadamard gate on qubit 32. So qubit 32 is, counting from the right, is this one here. And now we see the problem. So we need to perform 2x2 updates of this form. And we see that those two numbers, so those pairs of two numbers that need to be combined now, they are on separate GPUs. So for example, the one which has a 0 here is here, and the one which has all of these indices given by the same 0 and 1, but only this one 1, this is down here. So during the simulation now, we would, for example, need to combine this number with this number, and those are on separate GPUs, possibly even on separate compute nodes. And how can we solve this problem? The naive solution would be to transfer all these complex numbers so that the numbers that need to be combined are on the same GPUs. Then we perform the H operation, and then we transfer them back. And if you work that out, it requires, in this example, an 8 terabyte of memory transfer. And this is a lot of data that needs to be passed between the GPUs. So the optimal solution to do this now is not to transfer them back, but after we've transferred them once, we simply rename what we call a global and a local qubit and keep track of this so that later on, maybe we also might reuse it. So let's say we've done this swap now. So you see that the first GPU, GPU 0, now contains all the numbers which have a 0 here and a 0 at the very last one. So sort of the qubit Q0 here has become a global qubit because it takes part in identifying the GPU number. And now we can combine the complex numbers. So after we've done this exchange of 8 terabytes, all pairs of complex numbers that need to be combined are on the same GPU. We only need to keep track of what we call global and local qubits so that we don't make a mistake further on in the circuit. And this is the optimal solution. It requires to transfer half of all complex numbers only once and not back again. So how does this look in detail? So before the transfer, we have all the complex numbers in this form. The very first or the leftmost qubits identify the number of the GPU that they are stored on. And after this transfer that we need to do, it should be like this. So then this qubit has become a global qubit, and this qubit also needs to identify the GPU that it's been stored on. And we do this by building a buffer on each GPU. So we start with this situation. We have all these complex numbers on the first and these on the second GPU. And then we figure out what complex numbers need to be transferred. So in this case, it's all those numbers which have a 1 here, because what we want is that those which have a 1 here, they should reside on GPU 1 in the end. And on GPU 1, we identify all complex numbers which have a 0 here. And this always amounts to exactly 1/2 of all the complex numbers on each of the GPUs. And then we just swap them. And if we work that out, we see that whenever we need to make such a transfer, it's always the same. It's always that 2 GPUs need to exchange half of all their complex numbers. So in this particular example, it's GPU 0 with GPU 1 that they need to swap their numbers, but it could also be GPU 0 with GPU 255 and then GPU 1 with another GPU. But it's always pairs of 2 GPUs that exchange all the numbers. And after we've done that, we retrieve the numbers from the buffer and we're done with it. So that was a single qubit gate, but as you see in this circuit here, we also have 2 qubit gates. So we have certain gates that act on 2 of these qubits. One particular example is a very popular 2-qubit gate is the C0 gate. This is an acronym for controlled not, and what it means is it's described by this 4x4 matrix, and it means that if you identify the 2 qubits that it's acting on, like Q0 and Q1 here, then for all the indices where the control qubit, in this case Q1, is 1, it should swap with the corresponding number where the target qubit is 0. So it should swap the one where the target qubit is 0 with the target qubit 1, but only if the control qubit is 1. That's why it's called controlled not. This flipping from 0 to 1 and back is the NOT gate for a digital computer. That's where the name comes from. So let's look at this example. Let's say we are simulating a 4-qubit quantum computer. We have all these complex numbers here. And now, as we're simulating this gate, qubit 1 is the control qubit and qubit 0 is the target qubit. So at the moment, we have on GPU 0 all these numbers. On GPU 1, we have these numbers, and on GPU 2 and 3, we have these numbers. What needs to happen now is that we need to swap those numbers where the control qubit is 1 if their target qubit is the inverse of the other. So we have this one needs to be swapped with this one all the way up to GPU 3, this one with this one. And you see that this all happens locally. So in that sense, simulating a C0 gate on these local qubits is much simpler than simulating a global single qubit gate. So that's different from what you typically see. Also in an experiment, a C0 gate is actually the hard thing to build. Now on a supercomputer, when we simulate it, it might be that the C0 gate is actually very simple. So there's no communication between the GPUs necessary. Let's look at this C0 gate here. Now qubit 3 is the control qubit. And if you work that out, you see that this number needs to be exchanged with this one and this with this one. And similar thing happens on GPU 3. So also here, we can do all this locally on the GPU. There doesn't need to be any memory transfer between different GPUs. But this is not always like that. So let's look at this one where the control qubit is a local qubit. So in this case, local qubits are those and global qubits are these here. And the target qubit is a global qubit. Now, in this case, we need to swap these complex, this one here with this one, because here you see control qubit is 1, but the target qubit is different, and all the way through to here. So also in this case, we need memory transfer between the GPUs. That's the first case for a 2-qubit gate that we've seen. And this requires, in the end, a transfer of half of all the complex numbers that are on these GPUs. And then the last example is 2 global qubits. And also in this case, we would need to swap these complex numbers with these complex numbers. And what we could do now is simply relabel the GPU. So we simply call this GPU 2 GPU 3, and this GPU we call GPU 2, and then we keep track of relabeling. But for benchmarking purposes, and this is the topic of this talk, we do such an MPI transfer also to test the network whenever we have numbers on different GPUs. So we don't do this kind of optimization trick in this particular case. So where are we actually simulating these things on? The supercomputer or the GPU cluster that we used is called JUWELS Booster, and it is made up of 936 compute nodes, which are all connected in what is called a Dragonfly Plus topology. So we have groups of compute nodes in this funny arrangement here, and each of these groups contains 48 compute nodes, and each of these nodes contains 4 NVIDIA A100 GPUs. So this is where the actually GPUs are which do the computation. And you can imagine that passing data in between different nodes through this topology here is sort of difficult. But that's why simulating quantum computers is also interesting for the engineers of these computers, because it requires a lot of memory transfer, and then we can benchmark how well they did the connectivity between different GPUs on different compute nodes. So this particular system has 3,744 NVIDIA A100 GPUs, and it was benchmarked with a performance of 73 petaflops, which made it end up as number 1 in Europe and number 7 in the world. And also what is nowadays very important for environmental reasons is the green 500, where it's become number 3. So why can we use quantum computer simulators like JUQCS to benchmark these supercomputers? We've already seen that it's very memory intensive. So we fill up almost all the memory that exists in these supercomputers. So for the particular example we've discussed, 16 terabytes. Then these simulations are very network intensive because each global qubit gate needs a transfer of 1/2 of all the memory. So in this example here it would be 8 terabyte of memory transfer between the GPUs. And third, it has a very high GPU utilization. So for 40 qubits, we could either choose to put all those complex numbers in packages of 30 gigabytes on 500 GPUs, or all the way up to packages of 8 gigabytes on 2000 GPUs. So in this case, we could also benchmark the case where almost all of the GPUs take part in the computation. And conceptually, I find this interesting because now we're using GPUs to simulate universal QPUs. So such universal QPUs, meaning quantum processing units, don't exist yet, but we can use all the GPUs that we have to simulate what they would work like if they already were there. And we also did an application for all these benchmarks, which is solving airplane scheduling problems using a particular algorithm that's called quantum approximate optimization algorithm. So that is a family of quantum circuits that was invented to solve optimization problems on gate-based quantum computers. So here are some benchmark results. So we see the normalized runtime, so the runtime for different problems. And on the left, this is what is called weak scaling. It means that we increase the problem size. So we have 32 qubits up to 40 qubits, which already take a lot of memory of the supercomputer. And at the same time as we increase the problem size, we increase the number of GPUs that do the computation. And ideally, if we increase the resources, the computational resources, as we increase the problem size, we would expect, for perfect weak scaling, we would expect a constant runtime. Now we will see in a second why this is not exactly constant. But the most important thing is that it's not exponentially growing like this one here, because that would kill this application. So this is a logarithmic scale. So if a simulation of a slightly larger problem takes twice the time, we could not simulate very large problems. Then these two plots here show strong scaling results, and strong scaling means we keep the problem the same, so we simulate the same quantum circuit, either 34 or 40 qubits, but we increase the computational resources, also exponentially, right? We double the number of GPUs every time we go forward here. And then ideal strong scaling means that every time we double the number of GPUs, we halve the time that it takes to do the simulation. And for the 40 qubit problem, you see there's some curious thing happening here. And we see in a second what actually happens here. So this is how a quantum computer simulation finds when these supercomputers are not implemented or not connected in an optimal way, for example. So this is data that was taken during the early operation of JUWELS Booster when it was just being built last October. And this was valuable because then we learned what is actually not working very well in these connected GPUs. So this is the same data as before, but now plotted not in logarithmic scale, because then we can indicate what part of the runtime is used for the computation and what part of the runtime is used for the memory transfer between the GPUs. And you see for the weak scaling that the computation time is always constant. So that's the ideal case, that's the ideal result. So it could not be better. But you see that the transfer time between the GPUs increases linearly. And also this is to be expected because for a larger problem, there is more data that needs to be transferred. So this is why the graph on the previous slide was not exactly constant. And this is something that one could not work around. But the important thing is that it's not exponential. So that is how the simulator allows us to still continue simulating until, say, 40 or a few more qubits. And this is basically set by the memory, right? If we have another supercomputer with twice the number of GPUs next year or the year after, we can simulate more qubits. But basically, if the memory is not there, we cannot. And here we see the problem that we've seen on the previous slide, where the scaling is actually better than it should be. So we see that the computation time is halved as we double the number of GPUs, but the transfer time is, it improves by more than a factor of 1/2. So this reveals that when we have 16 gigabytes or 8 gigabytes on each of the GPUs, then there is something happening that's not optimal. And one reason for this, as I've already said, was the early access phase. But another reason is that the quantum circuit that we used here, which was the application to solve airplane scheduling problems, is not a very optimal circuit to benchmark supercomputers because it has a very particular sequence of quantum gates. So what we did then, of course, is to replace the circuit by an optimal circuit for benchmarking purposes. And these circuits are called Hadamard benchmark circuits. And they are very simple. So we have a Hadamard gate on all of the qubits that take part in the simulation. Now it's a 42 qubit simulation, so from Q0 to Q41, and then we repeat it 11 times. And for those who know about quantum computing, they might think this is a rather trivial circuit because if we have two Hadamard gates, one after another, then it's actually an identity gate. So if we do two of these sequences, then actually nothing has happened. But this is exactly what makes the circuit interesting. It's not only for benchmarking supercomputers, but it's also helpful to benchmark real quantum computers. Like you could benchmark Google's Sycamore chip with these circuits, because if you do something of which you know the result, you know that after applying all those gates a second time, it should go back to where it started, then you know the answer. And this makes these circuits very scalable. And in between, if you do it an odd number of times, the state is what is called a uniform superposition, which means that all of the possible bit strings from all zeros to all ones should be in the output with equal probability. So the relative frequency should roughly be all the same. So with these circuits, you can, in principle, benchmark all of these computers. You can see if they work as they should because you know the result. So the features, as I've said, is in this particular case 11 times H on all the qubits, and you see the ordering is somewhat strange. And the reason is we do all the global qubit gates first, because then we do all possible MPI transfers, so all possible data transfers between the GPU. And circuits that are made in this way, they're called identity circuits. So we have a bunch of these in this paper here. They are scalable because you can scale them to an arbitrary quantum computer size, and they are normalizable. So we have all the same gates here. So we know that roughly the computation for all of these gates is the same. And with these sort of optimal benchmarking circuits, we repeated the previous experiment. And now we see that for the weak scaling up to 42 qubits, now using 2048 GPUs, the computing time is constant and the MPI time increases linearly as before. So not much change here, but the important thing is that the data transfer or the overall runtime does not increase exponentially, which is typically associated with quantum computer simulations or also quantum computer operations in general. And now with these circuits, and this also happening after the early access phase of the JUWELS Booster supercomputer, we also see that this artifact has gone, that it's not better than it's theoretically supposed to be, but it shows ideal strong scaling. So it reflects that if you've looked at the simulation times, they've gone down. So it also reflects that the engineers have done a good job building the supercomputer. And the speedup that we found from the CPU-based version to the GPU-based version, this was an older supercomputer with NVIDIA Tesla V100 GPUs, was roughly a factor of 10. And then if we went to the new NVIDIA A100 GPUs, we got another factor of 2 to 3. So roughly a factor of 30 speed up with the increase in performance of the GPUs that NVIDIA did. But we see more of that in the previous application. So now in the next application, so now we leave the ideal gate-based quantum computer and we come to the simulation of a physical realization of a quantum computer. And a physical realization is, for example, this Google Sycamore chip here with the 53 qubits. So one qubit was dead, unfortunately, so it was not 54, but 53. And also IBM has these gate-based quantum computer prototypes. Typically, you see this dilution refrigerator here, which is basically a large fridge, which cools down the temperature here down to, say, minus, so almost to absolute zero. So it's only 15 millikelvin, so minus 273 point something degrees Celsius, so very cold. And only at the bottom of this fridge, you have the actual quantum computer prototype. So this is also a chip by IBM. It's a 5-qubit quantum computer. And to simulate this real chip, we have to do a bit more work. It's not just the 2x2 sparse matrix vector multiplications that we had, but it's a bit more complicated. What we do to simulate these chips in detail is we solve the Schrödinger equation or the quantum master equation that describes the behavior of this chip according to quantum theory. And if you work that out, that is a partial differential equation with a derivative with respect to time here. Then if you work that out, you see that it's composed of very similar sparse matrix vector updates. But, and that's important, we have many of these per time step. So we have some discretization in time to simulate the time evolution from when we turn the chip on to when we turn it off. And for each time step, we have to do a lot of these matrix vector operations. And they also have more than 2 states per subsystem. So before, we had complex numbers which had only 2, so 0 and 1 for each of these qubits, for each subsystem. Now the qubits are physical objects on the superconducting chip, and each of them can have more than 2 levels. And then we have also more physical objects on this chip. This is these resonators, only superconducting wires, and they can even have up to 1,000 levels. So it's not necessary to simulate 1,000 levels for these wires here, but maybe 100 or so, but definitely more than 2. And for the qubits here, we don't have 2, so we don't just, so these real systems don't just have 0 or 1, they also have a 2 and a 3 and a 4, so higher states, which are not wanted, so they disturb the operation. But if we simulate these devices, we of course also need to take them into account. And typically we take from 4 up to 12 of these higher states into the computation. And then the third thing which makes these simulations a bit more complicated is that these matrices that we do, they might involve the computation of a sine or a cosine function. So before we had simple quantum gates like fixed matrices already determined at the beginning of the computation, like this Hadamard matrix. Now we have a matrix which looks like this, and it involves the computation of a evaluation of a time-dependent function. And just for your information, this encodes a voltage pulse that is applied to these qubits. To do, say, a Hadamard gate, we have a certain voltage, a certain pulse that needs to be applied over time to make this Hadamard gate happen. And for the simulation, we also need to compute these functions here to evaluate the, to get the value of the pulse during the computation. And as you might imagine, these computations are very computation intensive. So it's of course also memory that's the bottleneck for the large systems, but also only for small systems where we have only 2 gigabytes of memory. This involves a lot of computation. So for benchmarking purposes, we use these simulations to measure single GPU performance. And now we can sort of judge whether NVIDIA did a good job in improving their GPUs. So here are some results. So we see the runtime versus the error of the simulation. It's of course always good to be able to scale down the error to reach arbitrary accuracy. Where I have to say that 10 to the minus 9 is sort of better accuracy than you could really measure if you're looking at an observable, like if you were comparing to some experiment. So that is perfectly fine. But okay, so we are looking at benchmarking. So we have an Intel CPU here. We see that's the top line, it's rather slow. So to reach an error of say 10 to the minus 4 is what we would want in a typical simulation we have to wait 1000 seconds for the simulation. Now, if we go to an NVIDIA GeForce GPU, rather old GPU, but still as we had it, we took it into this benchmark, we can already improve the time for the simulation by quite a bit. And now if we go to the NVIDIA V100 and A100, we see that it further improves. And what's the reason for that? The reason is that these NVIDIA GPUs have so-called Tensor cores, and they are very much designed to aid in these operations that we need to do. So we need to do those 2x2 sparse matrix vector updates. So this is of course a dense matrix, but on the whole, a bunch of complex numbers, this is a very sparse operation as before. And this is one thing where the Tensor cores really help in these GPUs. And the second thing is such operations. So that is a tensor operation that multiplies all these complex numbers. So one index of these complex numbers by a matrix which is larger than 2x2. So in this particular case, it's an m by m matrix. M is the number of states we have for each qubit. So not just 2 states for each qubit, but in real system 4 or up to 12 states for each qubit. And this is reflected in such operations on the GPUs. So now you might ask, why don't we have a difference between the V100 and the A100 GPUs? Did NVIDIA do a bad job in making these new GPUs because they actually are not really faster than the older GPUs? No, that's not the case. The reason for this is that we were simulating a very small system, or rather small system, with only 4 states for each qubit. So we were only taking into account the 0 and the 1 state for the qubit and the 2 and the 3 state, but not more. And there we see that the system is still small enough so that we don't see an improvement. The tensor cores are basically still doing the same in both of these GPUs. But what if we go to a realistic system now? So let's look at a system with 12 levels for each of the qubits. And as a reminder, now we have to do those 12 by 12 matrix updates on this tensor of complex numbers. And now we can see the difference. So as we go from the CPU to the GPU, there's an improvement of a factor of 2 roughly, but if we go to the V100, we have an improvement by a factor of 10. And then also, if we go to the A100, we have an improvement by another factor of 3. So here we can see that NVIDIA actually did do a good job in building those GPUs here. Okay, so summarizing, we've seen that all quantum computer simulations are actually nothing else but huge, sparse, and complex matrix vector multiplications. And because CPUs and GPUs are just built in the core to do those matrix, or to do any matrix vector operations, simulating quantum computers is a very versatile way to benchmark supercomputers, because it's very memory and network intensive, and the simulation of physical realizations is also very computation intensive. And we've also seen a huge speed up from the CPU-based simulators to the GPU-based simulators. So here at the bottom are a few references. I've tried to update them as best as I could, because at GTC 21 they were not all there yet. And with that, I'd like to conclude. So thank you for your attention.
Gosh, Dennis, thank you very much.
Yeah, you're welcome.
Let me just say, and this is meant to be a compliment, I had a few questions along the way, but it was kind of like listening to Paul McCartney singing Let It Be. You just don't want to stop the song. You know what I mean? You just don't want to lose the flow. But I've got 2 questions just to get it kicked off. One is just a trivial question. First of all, yes, all of our events are available on YouTube probably about 24 hours from now, and just watch the meetup link for that. But my first question is, in the NVIDIA or Intel or what have you, in the kernels, the programs running on the GPUs, do they have the trig functions built in there? Uh-oh, think I just lost Dennis. We'll give him a second to come. Oh, there you are. Thought we lost you first.
I think I was gone for a while.
Yeah. Okay. So, well, simple question. In NVIDIA A100 or V100, are the trig functions in the kernel? Are those GPU functionality, or does that have to be done on the CPU?
No, that is so the GPUs can do that. They have particular implementation of these operations, and if that had to be done on a CPU, it will also kill the simulation, because every time you need to do those evaluations of a sine or a cosine function, you would need to transfer all of those numbers back and do the computation on the CPU, and then all the way back to the GPUs, and the transfer between GPUs and the CPUs that manage the GPUs. This is actually the bottleneck for these simulations. So we always try to do as much as possible on the GPUs while having as little transfer between the CPUs and the GPUs as possible. Also, if we transfer between different GPUs. So in the hardware, they are connected by some NVLink something, which allows the transfer between GPUs that does not go through the hosting CPUs. So it goes directly from the GPU into some wire somewhere to the other GPU. So it doesn't need to go back to the CPU, and then from the CPU to the other compute node, and then back from this compute node onto the GPU. So that's always the goal, to do as much as possible on the GPU.
Yeah, and in that light, I remember, and I'm just learning about GPUs at depth, but there's memory within the individual GPU. Then there's a shared memory within I'm going to use the word bank, but I know that's not the right term, of a group of GPUs. And so, as obviously the further you get away from the GPU itself, the more costly the memory. But the other question I have, before others, hopefully you're generating some questions, folks, because Dennis's consulting time probably doesn't come cheaply. But so when you started talking about the simulating the physical realization of a quantum computer, I started asking myself, well, I mean, I can kind of guess why you would want to do that, but why would you want to do that? I mean, the way I see it, the model of, okay, it's just a matrix times a vector compute problem, and now what you've done is gone from that perfect world, if I may, to the very messy and error-prone world of a actual physical quantum computer. Dude, why would you want to do that?
Yeah, that's a very good question. It's also much harder, right? So the work that I would need to invest to do this. But the reason is the following. So this topic of quantum computing has been around for 30 or several decades, right? For 30 years or something. And by now we still don't have the big universal quantum computer that maybe was promised 20 years ago. And then we go ask ourselves, why is that the case? And to understand why it's so difficult to really engineer such a device, why it took Google so long to really build Sycamore, we can sort of go the other way and try to simulate what they are building, and then try to understand why what they are building is not yet a real quantum computer, or why does it only work as a quantum computer for 3 or 2 or 4 or 5 qubits, but not yet for 100 qubits. And that is exactly the reason why we go down to the electronics, why we really want to simulate the electronic device that they are building, to understand what maybe limits this approach, and also to estimate how long it's going to take, like to estimate the engineering efforts that need to be invested to finally be able to build such a computer. So yeah, in short, the reason why we are simulating the real device is to understand, and maybe also to learn or to propose what one could do better in a future project.
Interesting. I mean, at some level, you're trying to simulate Mother Nature in a sense.
Yes,
you know.
yeah, you can say that. Although I might have to stress that whenever we do such a simulation, we have a model for the system, and we of course try to stick to the model. We use like equations from quantum theory to build this model, but nobody says that this model actually really truly applies to what they are building. So we are simply trying to do the best that we can in simulating these things and probably doing a good job. But in the end, only the only real judge is that whether they can build such a computer or they cannot. So yeah.
Like kind of like Occam's razor, you know.
Yeah, right.
It's modeling, right? So
exactly, right.
But you're getting close. So, all right. Well, thanks, man. Anybody questions? Oh, we've got some in the chat. Let me. We do have the microphones available, please. But let me. Alain, cool. You've got excellent. We'll go to your question first.
Thank you. I've read a number of papers by various authors claiming that they could very efficiently simulate not perfect, ideal quantum computers, but real, noisy quantum computers with various methods, matrix product states, matrix product operators, or matrix product density operators. Is this something you consider worth doing as well? And what are your thoughts about the claim, the achievements of very efficiently simulating those quantum computers?
Yes, so the first thing I might want to say is that whenever we say efficient in this context, we always mean as efficient as we possibly could, but because we are simulating quantum theory, there's always this exponential increase in resources. And also when we simulate these systems, we also have this exponential increase in GPUs, for example. So in the end, this is always the showstopper, or this is always what in the end tells us whether we can simulate it or not. So efficient in that sense, also in all the other papers that are out there, it means efficient as efficient as we can, but not breaking the exponential growth down to polynomial growth. So the exponential scaling is always somewhere. So in my simulator, and the one that I just showed, it was in the exponential growth of the number of GPUs. So if you go from 2,000 to 4,000 GPUs, at some point you have to stop. And in other simulators, like in matrix product state simulators or tensor networks, as also Google does a lot of work with, you also have the exponential scaling somewhere. So in that case, the exponential scaling would be in the number of complex and number of coefficients that you are simulating. So in the application where I showed, we always have all the complex coefficients, but you might imagine a situation where maybe you only need one or two of these complex numbers at the end of the quantum circuit. And if you only need a few of them, then you can do tensor network simulations, and then they could be much faster. But as soon as you want to have all the complex numbers, or maybe more than 1,000, then the exponential scaling is hidden there. So then this approach would also be limited. So you can try to work around that, but it's always somewhere. So
thank you.
Dev, you got a question in the chat. Would you be able to do it? Use the microphone? Okay, well, let me ask the question that Dev has queued up. What is the sampling issue with benchmarking of quantum computer and related controversy with regards to the Google's Sycamore claim?
Yeah, the sampling issue is that so I can only, okay, of course I can only guess what he means by that, but one issue is that when you have all these complex numbers, you need to sample from the probability distribution that they describe, because in the end the Google chip would give you a bunch of samples, a bunch of bit strings, a bunch of zeros and ones. And when we have all these complex numbers in the simulation, the question is how to get these zeros and ones. And then we need to sample from a huge distribution described by all these complex numbers. And that is by itself also an exponentially hard problem. So we need to build the distribution function and then use a random number generator to sample from this distribution and to spit out these samples. So that could be one thing which I would imagine what Dev means by sampling issue. Another thing is that even though we use those complex numbers to describe the quantum computer, we cannot ever see those complex numbers. So when we have Google's chip, we cannot look at these complex numbers that maybe are somewhere inside or maybe they're not. And then maybe sampling issue, that means the possibility to get information on the complex numbers from the samples that we have obtained from the chip. So to sort of go the opposite way. So we have now a bunch of samples, a bunch of zeros and ones. And the question is, what were the complex numbers? What was the probability distribution that this chip actually sampled from? And this going back is, of course, not possible in principle, but we can get some statement which we, by some test, might make reasonable. And that is what Google did. So they did this cross-entropy benchmarking, which gives us a number of confidence that says, yeah, well, so as you can see, what this Google chip did is really the distribution, the probability distribution that is described by all these complex numbers. But you could not prove it, right? So this test is, it inspires confidence, and they do it very well, of course, but fundamentally you could never really prove it. So I hope that one of the things that I said was what Dev meant with this question.
Okay. We've got a question from George, and George, you've typed it in, but I know you're sitting comfortably in your chair. Dev said thank you, by the way. No. George, go ahead, ask it. I can't represent you. Go ahead.
I hope my microphone is working.
Yes.
Perfectly.
Yeah. My question was, how could actual quantum random number generation be integrated into these classical simulators? And to some extent, you answered that with respect to the sampling. So I guess my question is, could just merely having a actual quantum random number generator increase the accuracy of these simulations or the speed by guaranteeing that your sampling is more purely random?
So that is a controversially discussed thing. The question is, what does truly random actually mean? And basically, if something is random, it just means that you, as the one who gets the random numbers, you don't have enough information to describe why these random numbers turn up in that way. So if we have a pseudo-random number generator, as we use it on the supercomputers, or maybe even a hardware random number generator from voltage fluctuations on your chip, if you get these random numbers, as soon as you are not able to find a system that reproduces these random numbers, to find some correlation between those random numbers, as soon as you're at that point, these numbers look truly random to you. And this is the same whether you get random numbers from a quantum computer, or whether you get random numbers from voltage fluctuations on your chip, or you get them from a good pseudo-random number generator. The only difference is, for the pseudo-random number generator, you know that there is some function that deterministically produces those random numbers. So you know there is more information. If you had it, you could predict the next random number. For the voltage fluctuations, you could probably not. And also for what people call true quantum random number generators, at least with the knowledge that we have now, we cannot predict the next random number, so to say. But we don't know that for sure, right? It might well be maybe in, say, 20 years, we have more knowledge on how these quantum systems work, and maybe then we know what the next random number will be. So to address your other question, whether it would improve the accuracy of the simulation, no, it would not. The reason is that if I show you my simulation results, you don't know the random numbers and the deterministic generator that I used to have these random numbers. So you have the same information that is actually zero information that you would have if I had used a quantum random number generator. So for the practical purpose, this is all the same. So you could use a good pseudo-random number generator with a large period, say 10 to the 64th, I think what the good random number generators have, or you could use voltage fluctuations, or you could use a quantum random number generator. As soon as you don't have any information, all those numbers look the same random as the others.
Thank you. That is a lot for me to think about, but that elucidates the issue. Thank you very much.
Yeah, I can also, so one, I think there's a book called Numerical Recipes by Press, William Press, I think. He has he has a lot to say about random numbers. And he makes, in his chapter on random number generators, I think he makes this point perfectly clear. At least, I mean, in a sense, it's also a matter of, it's also like, it's an opinion, of course, but that's typically the opinion that computer scientists, or that those who actually work with these things have. Oh yes, very good, Tara. You found the book on Amazon, and it's also available online, I think, for free on Press's page, on his web page, I think. Yeah.
Yeah. Thank you. The motivation for my question is coming from a mathematical background. I always hear true randomness, provable, etc. And that to me sounds like you've constructed a perfect straight line or any of those things in physics 101, perfect frictionless pulley and all those things, and it doesn't exist.
Yes. So in my opinion, that is true. So the belief in the real true random number is, in a sense, just a belief. As soon as you don't have all the information, the number looks as random to you as it possibly can.
So related question, and this is not directly related to what you've been saying, but can one put bounds on the complexity of a physical system that's generating random numbers, to say, to use a bit of jargon, say that the Kolmogorov-Chaitin complexity of this black box random number generator is greater than something? Is that
yes.
feasible?
So in principle, you can do that. But the question is, what does it really tell you? So there are certain measures by which you could put bounds on the system. As soon as you go to a system that you describe with quantum theory, you always have these exponentially growing bounds. And in the end, whether you use some Kolmogorov test or whatever, you get a number in the end that tells you something that might give you confidence for the answer to the question that you asked. But it's in some sense ideal that you would ever find the answer that really proves that something is as complex as this or random as this. So it can always give you an indication, right? But as soon as you go to real physical systems, you have to believe that the model you are using for the system actually is truly correct. And this is in principle something one can never prove. So the models that we have are good, of course. Also, as Tara said, like you use Occam's razor there. But in the end, it might always be 10 years from now, you have a better model and you know much more. And then you say, oh, how stupid was I at that point? But yes, I mean, yeah, to answer your question, of course, you can use those bounds and to get an indication of the complexity of the system. You don't have to overinterpret the result.
Thank you, and also thank you, Terrell, for putting up that reference.
Oh, sure. Yeah, the free stuff is always better. All due respect to Amazon. Anyway, so I put a couple references out there. I think I got the right one eventually. Okay, cool. this is being broadcast on YouTube, and there's like a 30-second delay. So I'm going to ask if Lydia or Katie have any questions. So you go ahead and put them in the YouTube chat, and I'll try to get them put forth here. And speaking of Katie, but there's Kate online, and I've noticed you've been paying attention the whole time, you and your cat. So do you and or your cat have any questions for Dennis? By chance?
No, I don't. Thanks so much for having me. This is certainly above my level of understanding, but I'm really just interested in knowing what other people know about quantum. I'm in user experience, so I want to know what the user is going to be doing with all of these. So that's everything from model developers up to C-suites. So I'm paying attention to the chat and listening to the questions that are being asked, and I really appreciate you letting me sit in and listen, and my cat.
Oh, sure. And the cat, yeah. Yeah, well, welcome. So, I mean, Dennis has taken us down into the bowels of quantum computing, and I don't understand half of what he says yet either, honestly. He's been doing it for a decade, so I'm quite a few years behind him, but we've got recordings available if anybody wants to make a second pass. Anybody besides me, because I'll make a couple passes at this. Let me, if there are no more questions, let me, I'm going to put in the chat, by the way. Dennis, you've done your lab well, so pass on that compliment to your principal investigators in your lab. A lot of really cool work going on there, so kudos to you and the whole team. But in short, as I open it up, and the reason, my selfish reason for having you today is I'm curious. So you know, clearly the work you're doing today and the papers you published, you're benefiting from the work that's been done before you, and plus you've been working on this for a decade. So as they say in the stock market, what about a home gamer, a guy like myself? I mean, I would love to try to reproduce at some level on my own, not, take stuff from your paper, but try to take your ideas that you presented here, swapping the data from one GPU to the other and all that, and try to build something like this from scratch, even though, you guys, your lab there is decades ahead of anything I could put together. Is this something that a home gamer could, kind of try to work through the complexities of it? And let's say you've only got, 4 GPUs or maybe 16 GPUs to work with. Is this something that is humanly possible,
Yes.
as a learning exercise rather than a product?
Yes, sure it is. Probably it's good to start with small things, but I mean, you have basically 3 options then available that come to my mind. So as a home gamer, if you wanted to say use and try things on a quantum computer, you would go to the IBM Q, for example, where you could make an account for free, and they also have simulators. You might want to use their simulator and try to look into the code what it actually does, because it's available for free. Then there are other packages, Python packages mainly available from Google too. So from Google it's called Circ, from IBM it's called Qiskit, and these are good reference to when you're building such a thing to start doing it. Now they don't, as far as I know, they don't use GPUs. So if you really want to do it yourself on a GPU, probably it's also good to start with 1 GPU and then take maybe write a simulator for a 4-qubit system. So you have those 16 complex numbers, and the rules for when you simulate a quantum gate, the mathematical rules that you need to apply to these complex numbers, they're all documented in say Nielsen and Chuang's book, for example, also in our papers. And in principle, you could also with the slides that I showed, you could work out what each of these gates does to the complex numbers. And then on 1 GPU, you could of course implement all these operations. So you write 1 kernel for the H, for the Hadamard gate, 1 for an X gate, for example, and then you go build your quantum computer that way. So one reference that comes to my mind, there was a book called Quantum Computing for Computer Scientists, I think.
Yep.
That book step by step goes through building a quantum computer simulator, and it has in each chapter at the end there are some exercises, and if you just went through those steps, I think the book is very, very well written. At the end, if you just do all of these exercises on a GPU, in the end you would get a massively parallel GPU simulator as the one that I've shown. What's not in the book, of course, is the communication between the GPU. Yeah, exactly. Yeah, perfect. That's exactly the book that I meant. So if you implement all these exercises on a GPU, then the only thing to have two GPUs that you need to add would be to figure out when you need to transfer data between GPUs. And then you could, for example, use the examples that I had in the slides. And I think the slides are also available online, right, on your page. Or if not, I can of course send them to you.
Yeah, please send, and I'll upload them to the page.
Yeah. Right. So, and this way you could sort of step by step build up the simulator that way to do things yourself, right? Because I also think that really doing things yourself is the only real, the only true way to learn these things, right? So you can read a lot and watch a lot, but only by really doing it yourself, you sort of can understand it and work with it.
Agree 100%. Let that be a takeaway for today. Not the main one, but an important one. Yeah, I mean, because as you were talking, I'm a software guy, so that's the way I interpret things, and it looked like it was rather manageable in that, okay, I could see that going in a function here, and I forget about it, and that detail going over here, and then I forget about it, and it looked very modular. Module, I guess is the word for it. There is a question coming in from, are you okay on time, Dennis, first of all?
Oh, yeah, sure.
You're good? Sebastian, are you, do you have a microphone, Sebastian? Am I saying that right? Mr. or Miss Senge?
If not, I think I can answer this question from the chat. So
go ahead.
Joining really late, but has QQuantum already been mentioned? NVIDIA is also working on such an SDK. Yes, that is true. So we've also done some of these GPU efforts in collaboration with NVIDIA. And during the project, they of course also asked us what would be helpful in a QQuantum package to help us in these simulations. And so as far as I know, okay, first question, QQuantum has not been mentioned yet, right? I do have backup slides on that, but I haven't mentioned it yet. Second thing is the same as in one of the previous meetups by Terrell, QQuantum I think is not out there yet. So as usual, right, you can subscribe to a mailing list, right? But you don't really get access to. But also from inside information, I know that they are, or I think they are working on implementing some of these things. So there's one always repeating scheme in these simulations, always particular sparse in-place matrix vector operations. And on my wish list that I sent to NVIDIA some time ago, I put exactly these operations that QQuantum should have, because if there was QQuantum already and if they had these operations, then I wouldn't need to write all the kernels myself, right? So in developing those simulations, it would certainly help us.
Yeah, but there'd be no fun anymore. You just call there.
Oh yeah.
I mean, come on.
Right. You can always say that after you've done the hard work yourself, right?
Yeah.
It could have been easier, but then you miss out on the fun doing it.
Yeah, absolutely. Yeah, and from I think one takeaway I have in it about QQuantum, I'm all for it, but I think the marketing got in front of the actual operational people. The CEO mentioned it at the NVIDIA conference, GTC. And, many times in corporations that catches the operational people by surprise. They got to catch up. So I suspect it'll be a while before we see actually a QQuantum library, but who knows? Dennis will have certainly more insight on that because, the work he does. Hopefully they they take advantage of what your entire lab has been doing. We'll see. That's a different issue. Anyway, let me end. Any other last comments besides? I want to say one thing quickly. I see Kate, Sebastian. I've gotten lots of things in meetups over this past 18 plus months of why you can't turn on the microphone, but being in the gym is the first time I've heard that. So I'm glad you're paying attention to us while you're on the treadmill or whatever. Anyway, Kate, did you have something to say? You or your cat?
Dennis, have you had to interface with any business owners or innovation leaders about quantum and trying to navigate conversations that are based around the hype of quantum? Have you had that experience yet?
Yes, sort of. So one thing, for example, that's happening at Jülich at the moment is that we get a D-Wave quantum annealer there. It was actually supposed to have been there already, but okay, then came COVID and it's got delayed. And there's also a building from for a gate-based quantum computer from whatever company. I think a few companies, also IBM and Rigetti, have been. There have been some conversations, but I'm not involved in them, so I don't know what will be there in this building yet. But yeah, certainly there has been interaction with the companies. And also Google, right? Because for their quantum supremacy experiment, we also carried out part of the simulations to verify the results of their device. And also then, of course, there's also connection with smaller companies. Like there's a lot of startups, right, that go out into the world and try to start building their quantum computers. But so as far as I know, we don't have too much to do with them, but okay, there's a lot of stuff that happens which I don't know. So yeah, I think I am not qualified enough to give a satisfying answer to that question, right?
No worries. I appreciate your perspective. Thank you.
Yeah, for technical people to talk to business people, it takes a skill, and it's actually a profession. I suspect that's what you're into, Kate. There's a special magic that has to go on, you know, and transforming one concept to the next. But anyway, good question. Any last call for questions before we let Dennis back to his evening, I guess by now.
Yeah.
Anything else?
Yeah, it's 5:30 here in Germany,
oh,
so it's not yet.
Okay, so you still have some more work cycles left in you for the day. That's good.
Yeah,
That's
yeah.
good. Well, let me, so what's the next thing you're working on then?
So okay, I am working on several projects. So the one that I presented part of is JUQCS. That is the simulator for the physical realizations. We have put a small non-MPI version on our internal GitLab repository, and yeah, there's going to be a paper where we are in connection with some experimentalists to simulate their experiment and to have some results in there. And then in another project, I'm revisiting Shor's algorithm, so to say. So Shor's algorithm for factoring, because we thought maybe we could use this large-scale simulator to really factorize a few numbers and see how well Shor's algorithm would actually do in a practical application. This is a very interesting project, which we started, say, a month ago, and that's also the one that I will return to after this session, for example. And then there are several side projects which I think would go beyond what we have been discussing. But okay, those are the two most interesting.
And very cool. Very cool. Actually, Dennis, what you mentioned about the Shor's algorithm, we're working on a project here as well. We just started about 2 months ago, so we beat you to it.
Oh, cool.
But you know, we're incorporating some full timers into the project, and as well as some high school students as part of
really cool.
part of the experimental aspect of it. And maybe I'll talk to you offline about that sometime to see either we can get some advice from you or we can be an asset on your side. I don't know.
Yeah, sure.
These
Well,
high
we
school
can do
students
it.
are pretty smart.
No, I'm open for discussions. It's
Yeah.
interesting to hear that you're also working on it. I don't know, maybe we've been doing similar things, or maybe there's some overlap, or we can both learn from. I don't know.
Yeah, well, I think you've been doing it for a decade now. You know, when you started your studies, at least, we've been working on it much shorter than that.
Okay,
but,
you have several people working on it, so
Yeah,
it makes up for it, I think.
Deal. All right. Anyway, we could talk later. Anyway, thanks again very much. You know, great job. I learned something, a few things today, and had a great time recalibrating my brain according to the work you're doing. So I appreciate it a great deal, as do I'm sure everybody else online. Thank you very much, everybody. We'll see you again next time, whenever that might be. And Dennis, thanks again, man. Keep up the good work. And anytime you want to come back and maybe share your next paper, you know, talk about it. You got an audience here. It's not all about numbers, it's quality sometimes. So thanks again, everybody. Have a good afternoon or evening or day. We'll see you next time.
Yeah, thanks again. Thanks for having me. Thanks for inviting me, Terrell. It was a pleasure I don't think it was the first real live YouTube event. That maybe not the first, but the first in this with this kind of scope. So yeah, thanks a lot for having me, and all best wishes, and yeah, we'll stay connected, right?
Yep, please. Yeah. Yeah, this is your first live YouTube. I could turn this into an NTF and start to market that thing, if you're familiar, if you guys know what I'm talking about. A non-fungible token, all right? Blockchain stuff. Thanks. See you all next time. Bye-bye.
Bye-bye.